everybody knows him, and so.
Thank you for this brilliant introduction. But it's a pleasure to be here. I'm often in California at this time of the year, but I must say that with the fires, the rains, and politics, Florence is better than Los Angeles right now, so I'm very happy to be here. It wasn't easy to decide what to talk about. I kind of threw the topic conformal loop ensembles in the email, and then I regretted it bitterly. And I think it's a very difficult topic to talk about. It's very dry, it's not very physical. On the other hand, it's very central to modern mathematical physics, and it's a very good way to introduce all kinds of modern ideas dealing with algebra, like quantum groups, diagram algebras, combinatorics, conformal field theory, the bootstrap, and more. So I think at least pedagogically it should be useful, and you'll see what you think in the end. Important remark, I don't hear well. I hear, in fact, extremely badly. So shy questions from the back will be completely lost on me. There are two possibilities. One is to have the microphone go around, although in my experience, when people hold the microphone, they usually hold it here, which means it's utterly useless. Or we can have somebody repeat the questions with a loud, clear voice, like Filippo. Anyway, don't feel shy. Please ask questions, and if I don't hear, well, repeat. Okay? All right. So now, what are conformal loop ensembles? Let's start with a very simple example. In fact, in my own history as a physicist, I was reading this book about mathematical physics, and I saw the loop formulation of the Ising model, and I fell in love with that thing many, many years ago. So let's take the Ising model, whose partition function will be the sum over all the spins equal to plus or minus 1 of the product over nearest neighbors. Get used to these notations, by the way, of e to the k sigma I sigma j. So that's the Ising model, as you all know. Let's take it in 2 dimensions. On the hexagonal lattice, or I should say honeycomb lattice. So this is a lattice that looks something like this. I also draw extremely badly, I warn you, but I will have slides to illustrate my points. And then let's do a very, very standard thing, which is called a high temperature expansion, where we observe that because sigmas are equal to plus or minus 1, we can write e to the k sigma I sigma j as hyperbolic cosine k plus sigma I sigma j hyperbolic sine k. That's obvious, since sigma I sigma j is equal to 1 or minus 1, and the sum is equal to e to the k or e to the minus k. And this is chk times 1 plus hyperbolic tangent k sigma I sigma j. So we can rewrite the partition function z as the sum over all the sigmas of the product over the neighbors of 1 plus sigma j sigma k sigma I sigma sigma j sigma k tangent hyperbolic by k, and I factored out a chk, which is a trivial normalization constant. I don't worry about. And then we do an expansion. So the expansion consists in taking for each edge of the lattice either 1 or the hyperbolic tangent k factor. So what we obtain typically are diagrams like this. Diagram like this means I took the term thk sigma sigma for this edge, and that edge. Otherwise, I took the 1. We expand. we have 2 to the n terms, where n would be the number of edges. And then we perform the sum over the sigmas. So, of course, whenever we have a dangling edge like this, with its 2 sigmas attached, and we sum over sigma equals plus or minus 1, the contribution of the diagram disappears. But whenever we have a loop, like this, if we have a loop, each edge contributes 1 sigma for its extremities. So, for instance, here we have a sigma j coming from this edge and a sigma j coming from that edge. So we have a sigma j square, which is equal to 1. And therefore, we get a result which I think is totally obvious to all of you, that Z is the sum over all the loop configurations of THK to the power the number of edges, or I'll use B for bonds usually, okay? So that's a very simple example of what we will call a random loop ensemble with sum over configurations of self-avoiding, mutually avoiding loops. In that case, simply with a fugacity THK per edge. Okay, in general, we will have a fugacity per edge, which I will denote very often by K, just for simplicity, but for now, let's keep it as is. Okay, so that's the ground zero example of a gas of loops. And now this branches us into the very big topic of what we will call loop ensembles. So I call them in the title conformal loop ensembles, but the conformal part will come only later. And I will also restrict to 2 dimensions. Okay, so what is in general a conformal loop ensemble? Well, you see me coming. It is a statistical object, statistical ensemble of self-avoiding, mutually avoiding loops and the very interesting thing will be that we are going in general to, so first of all, the sum of a self-avoiding, mutually avoiding loops, I will just keep it implicit most of the times. I will just write sum over loops. We will all know what we are talking about. And then we will have a fugacity per edge. So there will be many Ks in these lectures. K is pretty much any coupling constant for me. As you will see later, their numerical values are not particularly interesting. So instead of THK, let's just call it K. And then, this is where the beauty of the problem will appear, we're going to allow for a fugacity per loop. So the Ising case is a very special case where the fugacity of the loops is 1. In general, we will allow for a non-trivial fugacity. So K is fugacity of edges. And N is fugacity of loops. Okay? So the topic, which has become a very large topic, as you probably know, first in physics, because many interesting problems can be reformulated as random loop ensembles. there exists a beautiful reformulation of quantum field theory due to Zimanzik, Fröhlich, Spencer, and others that is essentially based on loop ensembles. There are many recent problems in quantum, let's call it quantum information, that can be reformulated as loop ensembles of one type or another. And then, of course, there are more reasons to study them, in particular as probabilistic ensembles. And under these guise, as you know, the study of loop ensembles has given rise to 3 Fields medals so far, not all French, funnily enough, and more probably to come. So this is definitely a big topic. Okay, so this is the ground zero. Now, why are these interesting? Why should we worry about loop ensembles as opposed to, say, ensembles of clusters or ensembles of triangles, or you name it? Well, let's think a bit more about our Ising model. Now, we know about a lot of things about the Ising model. We know in particular that the Ising model on the hexagonal lattice, or whatever lattice, has, in the ferromagnetic case, ferromagnetic case. So let's take the ferromagnetic case to start. So I should be careful here, it's tangent k, that's positive. We know that this guy has an interesting phase transition. In fact, it has a low temperature phase. It has a high temperature phase. And these two are separated by a critical point. What's the low temperature phase? Let's start with the high temperature phase. The high temperature phase is, so K, of course, e to the k sigma I sigma j must be thought of as e to the j over t sigma I sigma j, where j is some coupling and t is a temperature. So high temperature means high T means very small k. Therefore, it is quite clear that at high T, our loop ensemble is not going to be very interesting. Tangent k is going to be very, very small. Most configurations that contribute to the sum will only involve just a few small boring loops. So typically, a snapshot of our system will look something like this. Then we're going to increase the temperature. As we increase the temperature, exponential k becomes larger. As we lower the temperature, exponential k becomes larger. This means there are more and more loops. And it so happens that at Tc, something very interesting is going on. At Tc, the loops become large. But more than this, the loops are interesting objects in themselves. They become fractals. The loop become large and, in fact, are fractals for a reason that I will explain in a minute if you don't see it. And that's very interesting because they have many properties as fractals. In particular, these loops become scale invariant. Yes?
Before I'm completely lost, what do the loops represent again?
I'm sorry, what are the loops?
What are they representing?
What are the loops representing? Well, in this high temperature expansion, nothing. They are just product of THKs. That's all they are. I can tell you about the dual expansion in a minute, but for now, they are not representing anything in particular. They're just loops. Sorry, yeah, it's a bit disappointing, but in this way of thinking, that's all they are, loops, okay? Now, we will see in a minute that we can think of this in the dual expansion, and then there will be these loops, boundaries of domains of spins of the same color. And then maybe this will appear a little bit more physically. But do not expect in general that the loops will represent much. The loops will represent mathematical physicists' fantasies, if you want. That's about it. Of course, in many cases, they will represent something. There will be trajectories of electrons. There will be, like I warned you at the beginning, this is going to be rather formal. All right, so the loop become large, and in fact are fractals. Fractals are scale invariant. Fractals are conformal invariant. I'll explain again what this means, but the important part will be that the properties of the loops at criticality are universal. They're universal, they're characterized by extremely complicated mathematical structures, and this is the things that we're going to be interested in. At low T, well, low T is a little bit difficult to envision. Low T is a lot of loops. So the loops also are large. They're also fractals. But in contrast with the critical point, they are very packed. They are what we call dense. So it so turns out that in the low temperature phase, the loops are also interesting. And we will see that in general, loop ensembles have two phases of interest. The critical phase, which is also called sometimes the dilute phase, and the dense phase. But let's not get too far ahead of ourselves. For now, we still have to believe that this claim is correct, and there's a very simple way to show you that loops at the critical point have to be fractals. This way is to simply ask ourselves, after having discussed the partition function, what about other observables? So we could, instead of the partition function, consider correlation functions. Let's imagine now we calculate sigma, should be careful with my notation, sorry, sigma j, sigma k, sigma I0, sigma j0. Suppose we calculate this two-point function of this Ising model in this graphical expansion, when it is the same business, the sum over all the spins of the product over jk of so 1 plus tangent hyperbolic k sigma j sigma k. But now we multiply by sigma I naught sigma j naught, and we divide by the partition function. So now let's think of our expansion again in the presence of this new term, which I will call a source term. And now remember the argument we made that whenever we had a diagram that was not a closed loop, it would have dangling ends. The dangling ends would correspond to sigma equals plus or minus 1. When we sum over sigmas, that diagram is killed and we keep only loops. Now, if we have a sigma I0 and sigma J0, this means that we are already introducing by hand, so to speak, a sigma I naught and sigma J naught. So now if we want to draw diagrams which involve all the spins in pairs, we need to have on top of our loops a line connecting I0 and J0. So now the two-point function of the spins in the loop ensemble becomes the same business, sum over loop configurations of tangent hyperbolic k to the power b, but these loop configurations now must also contain a line going from I0 to J0 over Z, okay, which I will represent diagrammatically by the sum over this kind of diagrams over the sum over only the loop diagrams. So we have now an ensemble where on top of the loops we have a line connecting the sides I0 and J0. So this kind of observable will be very common in loop ensembles. And why is it interesting to my general discussion? It is because we know, on the other hand, the behavior of the two-point function in the Ising model, and we know that in the high temperature phase it has an exponential decay, and we know that at criticality it goes like 1 over Ri0 minus Rj0 to the, in that case, it's known exactly, it's 1/4. So this power law decay of the correlation function of spins is very interesting from the general point of view of criticality and critical systems, which I assume you know a little bit about. What's very important about this is that it is scale invariant, it is a pure power law. It doesn't involve a characteristic length scale, and one can deduce from this all kinds of interesting properties, which I will probably go back to later, but so far it's the general introduction. In particular, the fact that this decays as a power law tells you that the typical length of the lines you can draw in the system is not fixed. There is no typical length. If there were a typical length for the kind of lines that you could draw in the system, the correlation function would not be a power law. It would have a characteristic length scale. If it doesn't have a characteristic length scale, it means essentially that the lines we can draw can be as long as we want. And that's a quick way to see that at TC, the loops become large and in fact are fractals. So I will get back to this a little bit more, but for now the main point is criticality in the Ising model means criticality for the loop ensemble, and that's geometrically an interesting question. So that's point number one. Point number two, these observables, there are many geometric observables, and this is one of the things that we are going to be interested in what follows. So, before finishing the Ising model, let me make a quick remark. So the way I introduced the Ising model was by doing the high temperature expansion. It is often useful intuitively to think instead of the low temperature expansion of the Ising model. So what is the low temperature expansion? The low temperature expansion consists in saying that if the temperature is very low, T is very large, physically, for a model like this, when K is very large, the sum is completely dominated by configurations where all the spins are up, or all the spins down. Let's say all the spins are up. So as T goes to 0, the sum is dominated by all spins up. And then we can start thinking about the model in a low temperature expansion by considering perturbations of the situation where all the spins are up. And perturbations of situations where all the spins are up are situations where a few spins are down. So we can think of representing the Ising model partition function now as an expansion where we identify here and there a few down spins. So let's do that. Let's imagine that this guy is down, this guy is down, and this guy is down. Now, it is interesting to wonder about the boundaries of the regions of down spins. What are the boundaries of regions of down spins? Well, they are conveniently written as loops on the dual lattice. So what is the dual lattice? The dual lattice is a lattice whose vertices live on the faces of the hexagonal lattice. And then, let's see I hope I'm not going to write something stupid. What we're going to do is draw a line crossing an edge of the hexagonal lattice whenever two spins differ. So remember, these indicate the down spins. These are the minus spins in a sea of plus spins. So I'm going to draw the domain walls. So here I have a domain wall, here I have a domain wall. Let's see. And then this is a minus, this is a plus. So here I have a domain wall. And here I have a domain wall, something like this. I'm sure my drawing is very bad, but you see what I mean. And here I have a domain wall, here I have a domain wall, here I have a domain wall. In general, what we would get are loops. On the dual lattice, which in that case is probably the triangular lattice. And the fugacity of the bonds is now not at all tangent hyperbolic k. It is the cost in energy for a piece of domain wall. Now, a domain wall is separating a plus spin from a minus spin. Therefore, with respect to the configuration where all the spins are plus, it is costing an e to the minus 2k. So we can reformulate the Ising model not at a high temperature expansion, but as a low temperature expansion, again as a loop ensemble. Z is again a sum over loops, not on the original lattice, but on the dual lattice. Of e to the minus 2k to the power the number of bonds, this time on the dual lattice. Yes?
I've seen some discussion of low temperature, high temperature for the Eisenhower.
Yes?
This part, lattice. Why you're using honeycomb?
Why isn't it the same lattice? Is your question, why isn't it the same lattice?
Yeah, why you're choosing the honeycomb?
Okay, I will get back to this. I'll get back to it. I'll owe you an answer, of course, but that's because on the honeycomb lattice, the loops don't intersect themselves. We will see in a minute that on the square lattice, they do. So bear with me. So for now, it's not nice. I agree it's not nice. I didn't want to do this, but then there was this question about what do loops represent. So, you know, that's... Anyway, it's interesting. All right, so yes, we're having two lattices. It's annoying. But I want you to realize, and you know this already, that the lattice is not going to matter. We're going to choose our lattice for convenience purposes. There will be a very solid universality of all this business. But for now, yes, I have a honeycomb and then I have a triangular lattice. Plus, really, my way of drawing the triangular lattice is really a shame, but that's okay. Let's get, yeah.
Now on the dual lattice we have how to say intersecting loops.
We're having loops on the dual, yes.
They intersect now. They are not.
No, I don't think they intersect because they are. Do they? Yeah, they may intersect. Yeah. Yeah. We will see that these intersections don't matter. Maybe I should have done this the other way around. Anyway, let's not worry too much about whether they intersect or not. The point I want to make is a bit different. The point I want to make is that the region where there are many loops is now the region where K is small, that is the high temperature region. So in the high temperature expansion, the high T region was a region with very few loops. And now in the low temperature expansion, the high T region is the region with many loops. So if you wish, one way to think of why this kind of region is interesting is if you think of it in terms of domains. And the question then becomes, in the high temperature region, what is the shape of the domains of spins? And you see in a high temperature region is almost trivial from the point of view of spins. The very large temperature region is completely trivial. All the spins are up and down independently. It doesn't mean that the statistics of domains is trivial. In fact, the statistics of domain in a high temperature region is highly non-trivial, because even if the spins are up or down randomly, domains can still have a very complicated shape. And here we're touching a very important point, which is that the reason ultimately that these models are interesting is because they are involving non-local properties. So the models, this model and other loop models are interesting because they involve non-local properties. Why non-local properties? Because the fact that two independent pieces here and there belong to the same loop is a question whose answer is non-local. Do these and that guy belong to the same loop? Well, in order to answer this question, I have to look at what happens everywhere and see whether I can connect these two bits by a loop or not. That's a non-local question. And it's one of the reasons why conformal field theorists are interested in these problems, because the non-locality is only mild, and as a result, they are described by manageable conformal field theories, which are called non-unitary and so on and so forth. And for probabilistic experts, of course, this is interesting because it's a non-trivial question. And in particular, the best way to see this business is to meditate a bit about what contours, what domain walls mean in the high temperature phases. And domain walls in the high temperature phase can be highly non-trivial, even if the spins themselves are non-trivial. So this is one of the interesting things to remember. And the other way to put this is to say that if we can reformulate all the variables of the Ising model as variables in the loop model, so I showed you how to expand the partition function, I showed you how to expand the spin correlation function. We could do this for all the observables. The reverse is certainly not true. So while the Ising model is a theory that's extremely well understood, the best probably interacting theory in the world understood, the loop model is not. Even to this day, the conformal loop ensembles for n equals 1 is not fully under control. It is an extraordinarily difficult problem. So when we go from the loops to the Ising, we really do a jump in magnitude of difficulty, again because of this non-locality. So when you do the simple thing of transforming spins into domain walls, we are in fact extending the problem by several orders of magnitude. And this is one more reason why we're interested in loop models. Okay? So all this about the Ising model. Now let's make a couple of extra remarks and then show you a couple of cute photos and have a break. So remarks. The lattice. Why did this guy choose the hexagonal lattice? Well, of course, we can do this on other lattices, and certainly the hexagonal lattice is not the nicest for many reasons. In particular, it's annoying to draw. It's certainly much nicer to draw the square lattice. See, even I can do a piece of square lattice rather comfortably. So what's wrong about the square lattice? Well, if we do exactly the same business, 1 plus hyperbolic tangent k, sigma I, sigma j, blah, 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 what we see is now we can have loops that intersect each other. Because the argument about having diagrams with one dangling spin killed and the others remaining now breaks down, because I can also have diagrams with 4 edges coming to a vertex. This sigma will come once because of this edge, once because of this edge, once because of this edge, and once because of this edge. So now I have the standard high temperature expansion of the Ising model on the square lattice. And by the way, if I wanted to do the low temperature expansion, I would do what I did before on my clumsy triangular hexagonal honeycomb lattice. And now it would be very easy. This would be the dual lattice. And I could draw walls between spins up and down on the dual lattice. Similarly, the walls would look like this. Okay? So is this bad? Is this not bad? Well, that's a very interesting question. So first of all, notice that although these loops intersect each other, they intersect each other very mildly. They only intersect each other at 4 leg vertices, and they only intersect each other once. I mean by this, they cannot go twice over the same edge. They cannot visit the same site more than twice on a given loop, right? So these things are often called trails, self-avoiding trails, something like this. And then the question arises, does this change the properties? Well, we know from the Ising model that the universality class of the Ising model on the square lattice and the honeycomb lattice and the triangular lattice and whatever lattice you want to imagine, regular, is the same in 2 dimensions. We know the exponents are the same, and in fact, it is a known fact that the universality class of loop ensembles at their critical point is not affected by these intersections. So when we write the loop ensemble, now we have to be a little bit more careful. I'm going to restrict myself to n belonging to the interval minus 2, 2, which means, by the way, I'm allowing myself to have n negative. As long as we're at it, we also, in fact, lately there's been a lot of interest in n complex, so thinking of these as physical models becomes a little bit difficult in these cases, but nonetheless, very interesting. And then we're going to say that we have typically 3 phases. So K small is the phase of small loops. It's not critical, we don't care anyway whether there are crossings or not. K equal Kc is the phase of so-called dilute critical loops. And now claim this critical point is independent of whether I allow crossings or not. I'm going to make a much stronger claim, totally unproven, but strong renormalization group arguments for this. Any model with whatever small amount of repulsion between bonds will fall into this universality class. That is, you could consider a model where you allow loops to go over edges twice, 3 times, 4 times, provided there's an upper bound. You could allow models where you allow loops to intersect themselves 1, twice, 3 times, provided there's an upper bound. Every time I claim you're going to have this universality class. The only case where you would not have this universality class is instead of self-avoiding loops, you had Brownian loops. Brownian loops would be allowed to go over the same edge an infinite number of times. So there's a different loop ensemble, a different universality class called the Brownian loop ensemble, which I'm not going to discuss because from a physics point of view, it's not particularly interesting. I mean, it's related to some interesting field theories, but it's much easier on a self-avoiding loop ensemble. So apart from this guy, any model with different geometrical constraints, provided they're mildly self-avoiding, will fall into this universality class. It's a super solid universality class, and you can guess this just by thinking of the Ising model. You know full well that there is only one universality class for the ferromagnetic two-dimensional Ising model. Another phase K greater than KC. So that one is really very hard. So this is called the dense critical loops. And now in contrast with the dilute critical loops, dense critical loops, well, they're more sensitive. So what are dense critical loops? I'll show you some pictures very soon, but dense critical loops now are sensitive to the introduction of crossings. So in fact, the universality class of K greater than Kc splits into two. There is the case without crossings, which is essentially the one I'm going to focus on. And then there would be the case with crossings of this type. And then in fact, there is even, depending on the lattice, another universality class where six-leg crossings occur. So this is extremely interesting. It's related with all kinds of beautiful quantum field theories. I'm not going to discuss this, but I want to mention this. Finally, the phase K equals infinity, which is sometimes called fully packed. So K equals infinity is really a bizarre phase where not only do you have a lot of loops, but you want to cover all the edges. Now this one is super sensitive to the lattice, super non-universal, and we're never going to think about it. Okay? So we're going to focus on the dilute and the dense without crossings. In this, okay, so finally some photos, pictures. Let's see. I was promised it would work. There we go. All right, so just to illustrate some very dumb points. Yeah.
It's a bit confusing to change L and B because otherwise it's confusing.
Can you repeat that? Sorry.
The partition function L and B should be exchanged, right? Because K should.
Oh, thank you, thank you, thank you. Yeah. Thank you. Yeah, maybe I could say at this point that soon we will see an algebraic reformulation of all these questions. And the question of whether you allow crossings or not has a lot to do with symmetry. So this is going to do, we're going to look at essentially three loop ensembles. The loop ensembles related to the permutation group, sorry, the symmetric group, the orthogonal group, and the unitary groups. And there will be different rules that will be dictated by the symmetry. Yes? Sorry. Yes. I'm sorry? Yes. You're asking about anti-ferromagnetic Ising? Is it your question? Think of it, homework for tomorrow. Anti-ferromagnetic would become K negative, so in this formulation it would correspond to a negative fugacity per bond. Yeah, I don't know. I never thought of it. Yeah, so it may depend a little bit on the lattice. As you know, in the Ising case, the ferromagnetic and antiferromagnetic are in the same universality classes, which we see essentially because loops have an even number of edges. So if we had a model with minus tangent k instead of tangent k per bond, in the end the partition function would be the same. So in that case, it doesn't make a difference. In general, the question of ferromagneticity or antiferromagneticity, I would reformulate in this context the question about the sign of K. And there are definitely things to be said. There are different phases. There could be different critical points for K positive and K negative or variants of this. Maybe I'll discuss this a little bit later. Okay? In particular, we'll discuss the Potts model and the ferromagnetic Potts model and the antiferromagnetic Potts model, hopefully. All right, so that's a nicer honeycomb lattice. That's a nicer square lattice. That's a cartoon of a loop ensemble. And this is a more sophisticated simulation, which is exactly at k equals kc. So it has a lot of loops, and you can see some of the loops have been drawn in color, and my main point here is to illustrate the fact that these loops are complex objects, they are fractal objects, and you shouldn't think that the loops avoid each other like this. The point is we have colored here some loops, but within each of these fjords, there are other loops, which maybe I can try to show by increasing the magnitude, and you see, I guess it's easy to see even though the colors are not very nice, but you see that within loops there are other loops, and if we kept blowing up we would have loops within loops and so on and so forth. So there are many obvious immediate questions you could ask. What is the statistics of the length of the loops? What is the statistics of the area of the loops? How many loops are there within a loop, and so on and so forth? All these questions are beautiful, and none of them are easy. So that's just an illustration. Here is the Brownian loop ensemble. That's the kind of thing you would get if instead of demanding that the loops avoid each other, they don't avoid each other. When you try to think of this kind of problem, very quickly you realize that it's not so easy to define a Brownian loop ensemble. You have to be a bit careful with the measure, but essentially this is how it would look.
Those are not bosons?
I'm sorry?
These Brownian loops, they are not simply bosons?
Yeah, so Brownian loop ensembles are pretty much bosonic field theories, yes. They're interesting. I mean, bosonic field theories in a sense are very difficult, right? So it's an interesting way to think of them, but absolutely, they're not very interesting as conformal field theories per se. Let's see, I wanted to entertain you by jumping to something we will discuss later. So there are many interesting limits of these conformal loop ensembles. A particularly interesting limit is when n goes to 0. So n goes to 0 is naively trivial, because when n is equal to 0 really, then z is just equal to 1. But if you take n very close to 0 but not exactly 0, what you're going to have, for instance, by looking at dz over dn at n equals 0, you're going to have the sum over the diagrams with only one loop, one self-avoiding loop, okay? So this is related with the physics of polymers in 2 dimensions and the famous n goes to 0 limit of de Gennes. So that's one of the few instances where the study of loops directly can lead to experimental predictions in the physics of polymers. That's at the critical point. But then you can also force dense loops. So what you can do is take one loop and force it to occupy a finite fraction of the lattice and ask you how it looks. And there's a claim. due to Nick Reed and myself, actually, that, and Jesper Jacobsen, that solution of the traveling salesman problem, in a statistical sense, are described by a gas of, well, by the universality class of a single dense loop. So here is a simple example of what we mean. This is Germany. Actually, it's probably the Western Germany. Any German here? No German here? Okay. You recognize. That's Western Germany, right? And so this is the solution of the traveling salesman problem for 15,112 cities. That's the red one. And the kind of question you can ask yourself is the following. If you give yourself a random distribution of cities and draw the solution to the traveling salesman problem, which is the shortest path going through all the cities, and you can ask yourself, how do the statistical properties of this object, what are the statistical properties of this object as you average over the distribution of cities? Well, the claim is that this is in the universality class of the dense critical loops as n goes to 0, in particular leading to predictions for critical exponents and so on. So if you want a typical example of a dense critical loop, this is it, traveling through Germany. I'm not saying it would be fun, but especially maybe in this region here, yeah, well, but you know. Anyway, good. Let's have a break and continue after the break. Sorry, yeah, I was just thinking, somebody asked, so to repeat, the Ising CFT, which anybody who knows a bit of CFT knows is easily solvable. The Ising CFT does not give you the fractal dimension of the spin clusters, right? The fractal dimension of the spin clusters is what's given by the loop ensemble, which is much more complicated than the Ising model. And I think it's discussed in this paper. Sorry, I don't mean to advertise my old works, but that's all I could think of right now, just to answer somebody's question. Okay, right. So now maybe I should cut to the chase a little bit. So we want to solve these loop ensembles. We want to know their critical exponents. We want to know a lot of things, and it's interesting, and it's not straightforward. All right, so there's a lot of technology, and I would like to start in a very classical way by discussing maybe the most natural loop ensemble from the point of view of statistical mechanics, which is the one related with the Potts model. So let's make a detour to what's called the Q-state Potts model on the square lattice. This is going to be a good excuse to justify the introduction of loop ensembles, dense phases, and then we'll be able to talk about temporal algebra and symmetric group. All right, so the Q-state Potts model is a model where the spins, instead of taking values 1 and 2 or plus and minus like in the Ising model, now take Q values, and the partition function is the sum over the sigma i's of the product over the neighbors of e to the k delta sigma j sigma k which means the delta means it's 1 if sigma j is equal to sigma k, and it's 0 over y. So for k positive, we're having a ferromagnetic interaction. We are favoring neighboring spins to be of the same color. And we're going to consider this model on the square lattice. Okay, so like we did in the Ising model, it is nice to do a high temperature expansion. By writing e to the k delta sigma j sigma k as 1 plus delta sigma j sigma k times e to the k minus 1. You verify that's true. If the delta is 0, this is 1. If the delta is 1, this is e to the k, so that's correct. And then we do the same kind of expansion that we did in the Ising model. We, for each bond, or I should say edge on the lattice, we either take the one or we take this term. So we draw on the lattice, and now you're going to be upset because I started with loops, and next thing you know, I'm abandoning loops, and now I'm having instead what we're going to call clusters, but don't worry, the loops will come back. So we're having in general an expansion with objects I call clusters. So clusters are made of edges and vertices. And observe in particular that that I count as clusters isolated vertices also. So these are clusters, and I count isolated vertices as clusters. So for instance, this diagram here means that for the blue edges, I took the e to the k minus 1 term, and for the non-blue edges, I took the 1 term. So if I have a vertex surrounded by only white edges, it sits on its own, but nonetheless, I must remember that it's there. That's why I drew it in blue. So this is a typical diagram we will get in this expansion. No loops. Instead, we're having an expansion in terms of clusters. And of course, in general, there will be various kinds of interesting objects that we could draw. Luckily, in 2 dimensions, they kind of all do all of each other, but in higher dimension, it would be much more complicated. Okay, so in general, this allows us to write the partition function as, and maybe it's time to introduce a microscopic amount of formalism. So I'm going to write this as the sum. So E denotes the set of all the edges of the graph. Here is the square lattice. E prime are subsets, all the subsets of all the edges. This is the subset where I took these blue edges, and otherwise the other ones I didn't take. And then what do we have? So what is the weight of these clusters? Well, it's easy. For each blue edge, I have an e to the k minus 1. So I have an e to the k minus 1, 2, and now I'm going to use the notation e prime to denote the number of edges. I called them bonds earlier. Sometimes I may call them monomers. There's really no uniform denomination in the literature, but here I'm going to try to be as careful as I can. And then we observe that a cluster is obtained by having a product of delta functions. So remember, if I took this term, it means these two guys have the same color. So if I have a cluster, all the spins on the cluster have the same color, and there's q such colors. So I should have q to the power, and I'll call it k of e prime, where k of e prime is the number of clusters. Okay? That's what I get. So, no loops. And we could, by the way, forget completely about loops and argue instead that we should look at cluster ensembles. In a way, they're harder. Really depends on how we decide their weight, but let's not do that. Let's just take clusters as an intermediary for the time being. So our goal now is going to be to transform clusters into loops. We can do that.
Excuse me,
Yeah. Yeah.
why did we throw away the ones?
Why did I what?
Why don't the ones disappear appear anymore? So we have 1 plus delta, but then we only consider the
1 plus delta sigma j sigma k e to the k minus 1. So if this is my lattice, either I take the 1, that's what I get, or I take the e to the k minus 1 delta sigma j sigma k, and then I sum over q. So in that case, I get q squared because I have 2 isolated sites. I said that isolated sites counted as clusters, and here I have q.
But in the expression for z, we don't have the ones, or
Sorry, I don't get you. Here this is subset with no edge, subset with one edge, and for a given subset, e to the k minus 1 to the number of edges, q to the number of clusters, again remembering that an isolated site is a cluster. Does somebody see what's not clear?
Perhaps it's e prime equals 0 is the first evolution.
You could write 1 to the power e minus e prime as a factor here, but since this 1 to the power is negative, it's just multiplying by the power of 1.
Sorry, can somebody help? Or? Okay, well, it's just an intermediate calculation anyway. If you don't get it now, we can always talk about it later. So let's transform the clusters into loops. So this is done in general using a bit of geometry by associating. So now let me blow up one face of the square lattice. So this is just one face of this lattice. And then I need to introduce what is called a medial lattice. So what is the medial lattice? The medial lattice has vertices which stand on the edges of the original lattice, and then in that case it's going to be another square lattice. Okay, so I'll draw it like this, even though the sides outside are not really, and these two edges are really just one, but I'll draw it like this for the time being. And then more generally, if I have a more complicated lattice, what matters really is what's inside. The outside sometimes is a bit confusing, but we can mostly focus about the inside, and then we're going to close it like this. Okay, so this is the lattice I define as the surrounding lattice. Its vertices, again, sit on the edges of the original lattice. And then when you look at the boundary, you close things any way you can. So you can think of these as independent vertices or not. It doesn't really matter. The point is that now, if we have a cluster on the original lattice, so this is a cluster configuration on the original lattice, we're going to associate with it what's called a polygon decomposition of the surrounding lattice. This sounds scary, but really it's completely trivial. What you do is you draw the boundary of the cluster on that lattice with the simple rule that these boundaries avoid the blue edges and they cut the non-blue edges. So morally, it's really exactly this. You just draw the surrounding polygons around your clusters. Draw the surrounding, I call them polygons, but then you've all seen that they are self-avoiding mutually loops. So the fact that it is drawn on the medial lattice and so on is of interest to graph theorists, but for us, there's really nothing to worry about. All we do is we draw these guys. Okay, so let me have one loop, one circuit, for instance. Okay, so these are my polygons. And now I have one inside and one outside. Okay, that's what I do. Boundaries of these clusters. Now this drawing is on the plane, and we will soon see that the genius of the surface we're on may start playing a role, but for now we're going to draw everything on the plane, which means no periodic boundary conditions, nothing, right, for the time being. Okay, no periodic boundary conditions for now. So again, I have my expansion, and I have a one-to-one correspondence between this expansion and the diagram, the polygon decompositions. And now I need to do a bit of geometry. So there are two relationships that I need to use. One I will call L of E prime is K of E prime plus C of E prime. So what does this mean? L will be the number of polygons or loops for a given diagram. K I defined is the number of clusters, and C will be the number of cycles of the clusters. I should say independent cycles. Now this looks scary. Let's do some examples. Here is an example of a diagram I get on my little square. So these are the blue bonds. Now I'm only drawing the blue bonds, clusters. Let's look at the surrounding polygons. I have one, I have two. Okay, so this is a diagram where I have two loops. How many clusters do I have? One cluster, another cluster, two clusters. How many cycles do I have inside the clusters? 0. Independent cycles, or I should say, drawn on the clusters. Okay. So that's one example. Let's do another example with a sexiest diagram. How about this one? So now this is 4 blue bonds. What are the polygons associated with this guy? Well, now I have 2 polygons. I have one inside and one outside. So I have L equals 2. K, how many clusters? All right. Time to involve the crowd. How many clusters? Hey, I have only these 4 edges. 1, of course. K equals 1. Now, how many cycles? Well, on the blue graph, there is 1 cycle, right? So this is 1 cycle. So C is 1. So again, L is K plus C. So that turns out to be always true. In general, a good way to count the cycles is you take a cycle in a graph connected or not. You take the graph and you look for the minimum number of edges you can remove so that all cycles disappear. And this gives you the number of cycles. For instance, this graph, how many cycles does it have? How many independent cycles? 1, 2, 3, 2. Thank you. Of course, 1 and 2. The third one would not be independent. It would be a combination of the other two, right? So that's completely easy. Relationship number 1. Relationship number 2 that I also need, it's that the number of clusters is equal to the total number of vertices of the graph minus the number of edges plus the number of cycles. You may think that this is related with the Euler's relation, and of course you would be right. So let's now look again at our first graph. K was 2. Okay, now what's V? Number of vertices, 1, 2, 3, 4. V is 4. Number of edges, 2. Number of cycles, 0. 4 minus 2 is equal to 2, which is equal to K, so that's good. Here V is 4. What's E prime? E prime is 4. V minus E prime is 0, but I have 1 cycle. C is 1, and I have 1 cluster. So it also works, okay? These things are, of course, always true, and they're really easy to prove. You start with a simple graph, and then you ask yourself what happens when you add a vertex. And that vertex can do this, or that, and you see what happens to these relations, and you see that they remain true, and that's a proof by induction. Very standard in graph theory. I don't think I want to do this in detail, because I want to go to the point. So what's the point? Point number 1, be careful. If you were doing this business on the torus, it wouldn't be true, these relations. We will see later what is not true on the torus. The point I want to make here is simply that when you start playing the game between equivalences of statistical models or, in fact, equivalences of conformal field theories, you have to worry about what happens to these theories on surfaces of higher genus. Dealing with the plane only, by the way, often the plane where you identify all the points at infinity is called the Riemann sphere. Dealing with properties on the Riemann sphere only is really not enough to make sure you've understood the theory completely. Anyway, using these two relations, I can write that K of E prime in my initial expansion, this number of clusters, which I didn't like because I didn't want to deal with clusters, I wanted to deal with loops, I can write it as L of E prime minus E prime plus V over 2. And now that's nice because I can reformulate my expansion, which was an expansion in terms of clusters. I can reformulate it as an expansion in terms of loops, what I wanted to do because I am loop obsessed. So this is Z, we can rewrite sum over E prime included in E of, and then we have, so E to the K minus 1, I will often call V for simplicity, V to the E prime, and then Q to the K of E prime, I'll replace by this, Q2 of L of E prime over 2. I get a Q to the minus E prime over 2, and I get a Q to the V over 2. Which is therefore, so V is a constant, I can factor it out, Q to the V over 2, sum over E prime included in E of, and now I get V Q to the minus 1/2 to the E prime, Q to the 1/2 to the L of E prime. Okay? So that's now a loop ensemble where the loops are not dilute, they're actually fairly dense, plus they're drawn on the surrounding lattice, so they have this rule of self-avoidance, right? They're kind of self-avoiding, but they're a little bit more complicated than the initial loops we had considered. But hey, they're still loops. They're still dense loops. In fact, in that case, they're fully packed, but it can be shown that they're in the universality class of dense loops in general. They have a fugacity Q to the 1/2. But then it's a bit annoying because there's this factor here, which is something to the power of the number of edges, and the number of edges can be expressed in terms of other things. It's not particularly nice, but if this is equal to 1, if e to the k minus 1 is equal to square root of q, then this factor disappears, and z is equal to q to the v over 2 sum over, now we can forget e prime, and this is just a sum over loop configurations of q to the 1/2 to L of E prime, which is just what I called earlier, L, the number of loops. So if we choose the Potts model at this particular value of the coupling, it turns out that we get exactly a nice example of a loop ensemble. And now, of course, this relation is just not an accident. Claim. This is exactly the so-called critical point of the Potts model. So this is something we could show by doing a little bit more of diagrammatics, looking at the dual lattice and so on. Maybe I will not do that. It's not very important for my purpose. The point is that there is a statistical mechanics model, the Potts model, which at this critical point can be reformulated as one of these loop ensembles. And the reason why we like it is that with Ising we only had n equals 1 and a dilute critical point. Now we're having all the values of n we want, because n, the fugacity of the loops now is just expressed as square root of q. And all of these are critical. So we have an interesting example of a dense, critical dense loop ensemble. So this is an example of realization of the dense universality class for the loop ensemble. In order to convince myself of this, however, I would have to convince myself that this ensemble is really very dense, but it can be shown that if you diluted it somehow a little bit, the universality class would be the same. So this is the claim again is just that this is a realization of this universality class. So to belabor the point, maybe, what we have in general is that you must think of these loop problems, so the loop phase diagrams, you must think of them as, so in general I called K the fugacity of the edges, and then there's a value Kc, And then there's all this phase where k is larger than kc. So all this phase is critical. That's what I've called the dense phase. And it flows to a certain critical point, which is a dense critical point, while the phase k smaller than kc is non-critical. So this is, again, the general shape of the loop phase diagram. If the fugacity of phases is large enough, you flow to the dense universality class. And then what happens is that this dense universality class sometimes is also realized by the limit k goes to infinity, which is really what we're having here. So if this sounds mysterious, just forget it and remember this is just one example of the dense universality class. If I wanted to dilute the model, what would I have to do? I would have to start adding vacancies to this problem. And in fact, it could be argued similarly that while the critical point of the Potts model is related with the dense universality class, the dilute critical universality class, the universality class you get when loops are fractal but not extremely packed, this fixed point corresponds to the tricritical Potts model. Okay, so we saw the loop ensemble again, the dilute critical fixed point, the dense critical fixed point somewhere there. I don't know exactly where it is, what it means, but there is a critical point you flow to when k is large enough. Two universality classes. They are realized in the Potts language as, respectively, the tricritical Potts model and the critical Potts model. Okay? So what's the point? Well, the point is, first of all, that now we have a physical realization of loop ensembles, not only for n equals 1, but for all values of n. I introduced loop ensembles by discussing the Ising model, which was n equals 1. Then I said, oh, we can generalize to other values of n. This looks a little bit abstract. But no, in fact, it is relevant. It is relevant to the Potts model. So it is perfectly natural to change the fugacity of the loops in the context of the Potts model. Point number one. Point number two, it is now maybe time to think a little bit in terms of symmetries. So the Potts model is a natural model with the symmetric group as a symmetry. Because the interaction is delta sigma I sigma j, so you can do any permutation of the colors. It doesn't change the Hamiltonian, the form of the energy. So this is a model with SQ symmetry. But now when we do this expansion and go on to a loop model, nobody forces us to take Q integer anymore. We can take Q arbitrary, we can take Q real, we can take Q complex. So we now have an extension of Potts to Q really belonging to the complex numbers. This means implicitly we have to ask ourselves the question, what is the meaning of the symmetric group when Q is complex? One of the reasons why people are interested in these models. So we're going to try to answer some of these questions, but that's one of the motivations for studying these ensembles. They are really a way to define models generically and to ask yourself about the meaning of all these symmetries generically. Okay, so the strategy will be to use tools known in the analysis of the Potts model to make progress on the physics of the loop models, even though, like I keep saying, the models for Q integer, the natural model we start with, are much simpler than the geometrical model we want to study. But it's also a good point to make connection with a few particular cases. So, connections with few cases. Well, first of all, if Q were equal to 2, the Potts model with 2 colors is nothing else but the Ising model. Well, if Q is equal to 2, sigma is equal to 1 or 2, e to the k delta sigma I sigma j is equal to e to the k if the two spins are equal, and it's equal to 1 otherwise. This is just like the Ising model. Same as Ising. So in the Ising model, I had e to the k sigma I sigma j, which was e to the k, let's call it k Ising, and let's call it k Potts. E to the k if the two sigmas were equal, e to the minus k otherwise. So up to a change of convention where e to the k Potts is equal to e to the 2k Ising, it is the same model. Ha! But in the Ising case, we saw that the critical point was the dilute critical universality class for n equals 1. Fugacity of the loops is equal to 1. That's what we saw, right? For the Potts, we see that we see from this argument that the critical point should be the dense universality class for Q equals 2. That is for a fugacity of loops square root of 2. Turns out to be essentially true. There are relationships between the dilute and the dense universality classes, and this is one example, an example that we will have to work on in more detail, but I claim that to a large extent, dilute loops of fugacity 1 are having the same long-distance properties as dense loops of fugacity square root of 2. Something very mysterious, but something that we can maybe elaborate on later on. So that's something that, if we work out our theory of the loop models consistently, we'll have to be able to check. How about Q equals 1? Well, Q equals 1 is particularly interesting because if I set V, which was e to the k minus 1, imagine now I set it to be equal to p over 1 minus p. And let's rewrite our partition function. So we had z, which was the sum, we had z, which was the sum over e prime subgraph of v to the e prime q to the k of e prime. And now if I define z twiddle, a renormalization, just 1 minus p to the e, where p is defined like this, sum over e prime included in e of, so v I've set p over 1 minus p, so it's p over 1 minus p to the number of edges times q to the k of e prime. And now let's take q equals 1. So this factor disappears. And what I see is that z twiddle is the sum over E prime, a subgraph of E, of P to the E prime, 1 minus P to the E minus E prime. And now what is this? This is exactly so-called percolation problem. We're taking a given subgraph of, we're choosing randomly subsets of E subsets E prime of E with probability P per edge chosen, and therefore 1 minus P per edge not chosen. Okay? So this is a problem where you take a lattice, in that case the square lattice, and then you sum over configurations where you choose edges at random. So you color them in blue with probability P, and you color them in white with probability 1 minus P, which is really a totally trivial random process whose partition function, of course, is equal to 1, because each edge can be chosen or not. So if it's chosen, it comes with probability P. If it's not chosen, it comes with probability 1 minus P. 1 minus P plus P is equal to 1. Z equals 1, of course, it's a probabilistic problem. Okay? So the partition function is 1, is trivial. Does it mean that the problem is trivial? Of course not. The problem of percolation is infinitely non-trivial, because what we're interested in is not the partition function, we're interested in various correlation functions. In particular, in the percolation problem per se, you are interested in whether there is percolation. That is, you're interested in whether there is some cluster going from top to bottom. And that question is non-trivial. And answering and finding out the probability of the cluster, the properties of the cluster is also a question that is non-trivial. And we can say something about this question, because we saw that the critical point was e to the k minus 1 equals square root of q, where, to be honest, I told you the critical point was e to the k minus 1 square root of q, which in that case means 1. So if we use e to the k minus 1 is p over 1 minus p, we see that the critical point of the percolation problem is p equals a half on the square lattice. Not a surprising result by symmetry, by duality. Nonetheless, it's good to see that. Okay? So of course we know that loops are dual to clusters and clusters are dual to loops. So the critical point for percolation means there's an incipient cluster going through the whole system, very tenuous cluster of vanishing fractal dimension. Well, sorry, fractal dimension smaller than 2. But now we can also think of it in terms of loops. This incipient infinite cluster has, well, a surrounding loop. And that surrounding loop is as interesting an object as the cluster itself. It is called the hull of percolation. So clusters, loops, once again, are dual, and that's just an example of a problem whose partition function is trivial. In fact, all the correlation functions at q equals 1 are exactly trivial. There are none, unless you start asking for geometrical properties, and then geometrical properties which can be expressed as derivatives of the partition function when q goes to 1 become extremely non-trivial. Yet another example, how about q equals 0? Q equals 0 is also interesting. Of course, as q goes to 0, we can consider z over square root of q, and that we see is that it's the sum over coverings of the surrounding lattice with only one loop. Why? Because each loop comes with a fugacity square root of q. The more loops, the more square root of q. The leading term would be 1 square root of q. That's one loop. What are the coverings of the surrounding lattice with only one loop? Well, if I want only one loop, I have to be very, very careful. I cannot have any cycles in my graphs. And then I must cover every vertices. Because if I don't cover a vertex, it's going to be surrounded by one loop. So what I'm going to get are trees. And then there'll be only one loop. So the number of coverings of the surrounding lattice with only one loop is equal to the number of spanning trees. Trees means subgraphs without loops, and spanning means they cover everything. Okay? That's a beautiful problem. Solvable, actually, which is related with free fermion theories, so that's some limit that's extremely interesting. Okay, 2 minutes and then I'll be done. That's okay? 2 more minutes? Like we expressed, remember, the 2-point function of the Ising spin was the sum over diagrams where there is a line connecting the two spins. We can ask ourselves about Potts order operator. I just want to quickly go over this, the Potts order operator. So in the Ising, the Potts order operator was sigma equals plus or minus 1. In the Potts model, it turns out that the order operator, which I'll denote quickly by Tj at side j, it's a tensor which is equal to delta A sigma j minus 1 over q. So that's essentially related with, so it's a number which is 1 minus 1 over q if the color of the spin is equal to A, and if it's minus 1 over q otherwise, you see that for q equals 2, it's 1/2 or minus 1/2. In fact, for the Potts model in general, it is this. And what I want to get to is that the 2-point function of the tensor, which is really what I'll be interested in later on, is 1 over q, delta AB minus 1 over q. None of these are very interesting. What is interesting is the next term, which is that's the sum over configurations where I0 and J0 belong to the same cluster. So this is really where I wanted to get to. In the Ising model, the order parameter 2-point function is the probability that the 2 points are extremities of a line connecting them. In the Potts model, the 2-point function of the order operator is related with the probability that the 2 points belong to the same cluster. It's kind of natural. They cannot belong to the extremities of the cluster. There is no such thing as extremities of clusters. So what you want to do when you look at the 2-point function of the order operator is look at the probability that 2 points belong to the same cluster. Okay? It doesn't mean, again, that they're extremities of the cluster in any sense whatsoever. They are just in the same cluster. which means in terms of loops that there is no loop separating them. So this is the same as the sum of the configurations where there is no loop separating I0 and J0. All this to express the fact that there's a bunch of interesting quantities in loop models. In loop models, you can be interested in probability that points are related by a line. You can be interested in probabilities that 2 points belong to the same loop, or you can be interested in the probability that 2 points are not separated by a loop, which means equivalently that they're both within the same loop. So there are all these different questions, and all these different questions are going to let us, well, should let us introduce different fields in a conformal field theory, and then ask ourselves, what are the critical exponents associated with these fields? What is the operator product expansion? And all that. Okay, so thank you for your patience. I'll stop now.